I think I couldn't have had a better intro than the previous talk that we had. So I'm going to talk about the problem of privacy in the context of data collection in mobile phones, but software applications also apply to IoT devices. So we all use recommendation systems. You coming to Niagara Falls probably use TripAdvisor to figure out interesting places to visit, or use Yelp to figure out which restaurants to go to and eat. And usually when you use this applications, the way you do it is that you install the application, it will request some type of private information from you. For example, in the case of Yelp, it will be your location. And then it will present you with a list of recommendations based on the data and feedback that is collected from other users. And not only you can see this data, but you're also recommended to give back to it, to either check in or give rating and write reviews. But thinking about how you interact with these applications yourselves, you probably know that you rarely provide that feedback to the application. Most of us are just users of these applications that don't really supply them with the information that they request from us. And that kind of shows when you look at the results. We're in the touristy spots, so it might not be that obvious, but if you move out, let's say drive out like 15 or 20 minutes, you see that the top ranking places will have tens, sometimes 100 reviews maybe. And then if you move down the list a little bit, toward but not that far, we're still in the top 20, you will see that there are places there with only a handful of reviews. 3 reviews here, 5 reviews there, and they are one of the top 20 places. And the fact that they haven't done grow probably shows that they have more customers than that. Now, the state of the art for these recommendation systems is that they rely on user interaction and feedback. And that is the main reason that we have this data sparsity problem in these systems. There's also, of course, another approach, and that is this coarse-grained data collection. And that would be for Yelp application to just collect your location all the time, and then based on your movement, figure out when you're visiting a restaurant, and just do a check-in automatically for you. But there are obviously privacy concerns with that, and users are uncomfortable with it giving that much detailed information to the Yelp platform. So we wanted to study how deep this problem is and see if we can come up with a solution for that. And the first step that we took was to do a measurement study to see how much data sparsity is really a problem in these platforms. We look at 5 different services: Goodreads, Yelp, Google Play, IMDb, and YouTube. And we took a random sample of the entries that exist there and looked at the number of interactions, whether it's the number of ratings or Lenovo updating itself, or up and down thumbs in the case of YouTube. Now, the results that we got were pretty surprising. This is a CDF of the number of feedbacks these services receive. And for example, looking at the graph, you can see that more than 50% of the sample that we had in Yelp have less than 10 reviews. And in the case of YouTube, for example, you see that 60% of them have less than even 5 feedbacks or up and down buttons. So one argument might be that, well, maybe if only like less than 5 people are providing ratings for a YouTube video, maybe not that many people are watching that video either way. So maybe it's just the number of interactions is low as well as the number of feedbacks. And on 2 of these services, we could actually get a sense of that. On Google Play, we could look at the number of downloads. In the case of YouTube, we had the number of views for each video provided by the services to us. And when comparing that to the number of feedbacks that they were receiving, we saw that there are orders of magnitude difference between the number of interactions that these services were receiving and the number of feedbacks that were provided by the user. And these are, in a sense, services that's very easy for the user to provide feedback. In the case of YouTube, it's just a thumbs up or thumbs down. Or in the case of Google rating, most of the time it's just like a 5-star rating. And these are technology services which users are more will provide more feedback to compared to other services. So there's a huge discrepancy that exists here that could potentially be filled out by using those implicit signals if there wasn't that many privacy concerns there. So that was the problem that we decided to tackle. How to allow privacy-respecting fine-grained data collection in these platforms. And an example of that would be for the case of the Yelp application that we were discussing. We want Yelp to be allowed to collect the user location, but only if that location is a restaurant. And we want to ensure that at the other times, the Yelp application or the Yelp service can't send out the user location to the cloud service. Now, before I discuss our solution to this, first I'm going to discuss how normally such an application would be written. So we would have an application, let's say we call it Yelp Data Collector, and it will ask the location service for user location, and it will ship it out to the cloud server. And later the cloud server either has a database of restaurant locations or will talk with another service, just Places API, and figure out that, oh well, yes, this is a restaurant. And they mark that as the data point. But the problem, of course, is that you're shipping out your data all the time, and you want to avoid that. So to do this in a privacy-respecting manner, we came up with a primitive that we call an immutable blob. And the immutable blob has three parts. For the first part is a JSON data structure. This could be either coming from one of the sensors that exist on the device. For example, the GPS sensor will give you something like latitude, longitude, the time. Or it could come as a response of one of the REST API queries to a list of trusted services. For example, so in our system, because we're using Android, we have Google API as a trusted API. And one of the responses that we put here as an example is the Google Places API, which will provide the latitude and longitude to, and will provide with the answer of what that location actually is. The second entity is the path, and the path allows us to point to one of the pieces of data that exists in that JSON data structure. For example, if you want to point to the value restaurant, you can say Google Places, Google APIs, places, results, type. And that can point you to the restaurant. And finally, we have a SHA-256 HMAC signature of the JSON data structure. And having that signature allows our system to verify that the data it's giving to the application is not modified by it. So the way our system works is that the developers will write a collector for the type of data they're interested in our framework. Our framework runs this collector inside the sandbox. We don't need to know what the collector is doing, what algorithm it's performing to provide its recommendation, but just a black box for us that we control what data goes in and what data goes out. So Heimdall provides this collector with a set of secure APIs to connect with other sensors and also the trusted services. So if the collector wants to get the user location, it will ask a secure API for the user location, and it will provide it to it in the form of immutable blobs. Now, if the collector wants to get some context for the data, for example, contact our trusted Google Places API, it has to send the parameters in the form of the immutable blob. And this allows our system to ensure that the collector is just not asking for a random location, and it's definitely a location that the user has been to recently. Then our secure API gets that data, it will ask the Google Places API for the data, we'll get the response, we'll convert it again to an immutable blob and provide it to the sandbox. Now the sandbox, using this data, can figure out that, well, this data has the characteristics that I need. This location is a restaurant. And it will ask Heimdall to submit this data to the cloud platform. Now Heimdall has a policy checker that can verify that the data that is getting shipped out matches the requirement that has been put on it during the install time. And we'll provide a more definite example in the later slide. And then, if the data it's shipping out matches the policies, it will transfer it to the cloud server. The interesting thing about this scheme is that this data that sends out to the cloud server does not necessarily have to be tied to the user identity. So if you think of an example where you want to know what is the best physician to visit around town, you don't necessarily need to know who are the people who are visiting each physician, and people are uncomfortable with sharing that data. But if this submission is being done anonymously, you will have an overarching view of the number of people each physician is visiting, and so you will have a better idea of which one you want to go to and visit. Now, the policy checker, with the form that we described, allows us to have very, very complex definitions of the data that is being shared. For example, in the case of the Yelp application that we were discussing in our presentation, you can say that you can submit the Google Places results name if the Google API's place results type is a restaurant. So you ensure that you can only share the name of the place if the place is a restaurant. And in our paper, we discussed that we support other relational constraints as well. Now, in our evaluation, we look at 3 different factors. One is the performance of the Heimdall. One is how it affects the user concerns. And finally, can we develop useful applications? So I'm only going to discuss the first and third item here. For the applications that we implement, which covers both IoT and mobile space, I direct you to the paper. Now, in terms of performance, we looked at 2 different factors that affect the performance of Heimdall. One is the blob generation time. How long it takes for us to generate one of those blobs, because on every interaction, we are generating one of those blobs to transfer data to the collector. And what we saw was that even if the JSON data that we're sending it is as large as 10,000 characters, it takes less than 350 microseconds for it to be generated. And the other factor we looked at was call latency. How long does it take for a call to go through? And we saw that even with 10 parameters, the call latency is less than 4.1 milliseconds. And we think that for the type of applications that we're talking about, these data collectors, these are acceptable overheads. Next thing that we want to discuss is did Heimdall really decrease the amount of concerns users had? And to measure this, we did a small-scale user study using the Amazon Mechanical Turk. We asked 166 participants how concerned they are on a 1 to 5 Likert scale about different scenarios. So we looked at 3 different scenarios. One was the location, and we asked them how much concern they have if an application is reporting their location all the time, only when they're using the app, or only providing the service with the name of the restaurant. On the purchase history, we asked them how concerned they are if the user, or if the system is collecting user purchases all the time, or is collecting only the food purchases. And in terms of browsing history, we asked how concerned they are if the application reports all their browsing history to the cloud, or only the website associated with a restaurant. In the location browser history, we saw a statistically significant decrease in the amount of user concerns in our results. In purchase history, we didn't see, we saw a decrease, but it wasn't statistically significant. And our hypothesis is that this is because sharing purchase history is not something that current applications are doing, and none of the current applications really have access to that type of data. So it might be a more unknown territory for the users. So on the misspelled summary, in this work, we empirically show that the recommendation systems suffer from a sparsity of data. We implement a system that we call Heimdall that allows us to control what type of data we're sharing. And this allows this recommendation system to start collecting implicit signals that are generally lost to them. And finally, we show that Heimdall has an acceptable performance overhead and significantly decreases the user's amount of concern.
Thank you, and I would love to take some questions.